This is number 1 from AP FRQ review, limits continuity. This is a non-calculator question. So we have a piecewise function defined by f of x. You have 1 minus 2 sine x that's existing to the left of 0. And then to the right of 0, you have another graph e to the negative 4x. So part A, show that the function is continuous at x equals 0. So if we want to show a function is continuous, we have to consider and step through our conditions. So the first condition is, does the point exist at C? The second condition, does a limit exist? And in this case, we have to dig a little deeper into the second condition. We have to look at one-sided limits because we have two separate graphs defined on either side of our C value. And then finally, if both tests passes, or rather, if the second test passes, we move to the third one, which is, does the point exist where the limit exists? And if the point exists, the limit exists, and the location of that point is where that limit is leading us towards, then we're guaranteed that the graph is going to flow through that point continuously. All right, so our C value is 0. That's the target x value, and that's also the value that we see here where there could be a split on either side of 0. So first thing, does f of 0 exist? Well, f of 0 is defined with the first piecewise function because we see the less than or equal to, right? That equal sign indicates that we plug 0 into the first function. So we plug 0 in, we get 1 minus 2 sine of 0. Sine of 0 is just 0, so 1 minus 0 equals 1. So first condition passes. Second condition, does a limit exist? We see that we can't just rely on one limit statement because we have two separate graphs defined on either side of 0. So we have to move to one-sided limits. We have to look at the limit from the left side of 0, and we also have to look at the limit from the right side of 0. So we have that notation there to indicate that we're coming from the left side of 0. But when you evaluate a limit, you're just going to plug that number in. You're going to ignore that that one-side limit, so you're not going to do any decimals or anything. This is just more notation to indicate that we're approaching 0 from a particular side. So if we plug 0 into the limit expression, we get 1 minus 0, which is 1. So the limit exists at 1. If I evaluate the limit from the other side of 0, again, just plug 0 in. So 0 plugs in for x, and we get e to the 0, which is 1. And so the limit exists at 1 from the left side of 0, and from the right side of 0 it also approaches 1. So we know that the limit does exist since we have agreements, an agreement on both sides of 0. So since the limit exists at 1, we can move to the next condition. The third condition, does the point exist where the limit exists? Okay, so we plug 0 in. So basically, this third condition just means that we're going to compare the results of the first two. So the first result is 1. The second condition gives us 1 as well. So we see that there's an agreement. The first two conditions are equal to each other. So therefore, our function is continuous at x equals 0. Okay, for part B, when x does not equal to 0, express f prime as a piecewise function. So f prime means that we want to find the slope formula on both sides of 0. So we're going to find the derivative of the first piecewise and find the derivative of the second piecewise. So first piecewise, derivative 1 goes to 0, 2 sine x becomes 2 cosine x. And the derivative for e to the negative 4x becomes e to the negative 4x times negative 4. Okay, so then we test which piecewise function can be set equal to where f prime is equal to negative 3. So we want to find out, find the value for which f prime is equal to negative 3. So we can set both f primes equal to negative 3 and see which one is going to be a statement that is true. So here we said negative 2 cosine x equals, I should have a negative here, equal to negative 3. And we see that this is not going to be true because cosine is always going to be greater than 0. right? So for x's, this is only true for when x is less than 0. We know we're also cosine is going to oscillate between -1 and 1, so we're never going to get that -3. So we know this first option is not going to be true. For the second option, if we set the second piecewise equal to -3, we can divide both sides by -4 to move that -4 over. The two negatives become positive. We take the natural log of both sides to allow for that exponent to come down. And now if we divide both sides by -4, which is the same thing as multiplying by -1/4, we get x equals -1/4 natural log of 3/4. That's a valid x value, so that is going to be the solution for x. Okay, find the average value. So average value of a function is going to be applying this average value theorem, 1 over b minus a, integral from a to b. But we see that there is a split at 0, so this f of x is just not going to be one expression. It's going to have to be divided into two separate regions because we have two separate graphs on either side of 0. So this integral from -1 to 1 has to split up into -1 to 0 for the left piecewise function, and then integral from 0 to 1 for the right piecewise function. So for the first piecewise, we're just going to go through our antiderivative step. X becomes 1, 2 sine x becomes 2 cosine x, or -2 cosine x. We evaluate our upper bound, followed by lower bound. Upper bound gets plugged in first. We get 0 plus 2 cosine of 0, minus big parentheses, and then we evaluate the lower bound. So -1 goes in for x, -1 goes in for the x within the cosine, and then we'll clean this up a little bit later. Let's look at the second antiderivative. Now, e to the -4x requires u substitution, so we let the u value be -4x. du over dx equals -4. We get dx equals du over -4. We get everything in terms of u. The -1/4 comes out in front, and the antiderivative of e to the u is just e to the u. And so we can replace the u back in terms of x. Then we can evaluate our upper bound followed by lower bound. Upper bound gets plugged in first. We get -1/4 e to the -4 minus big parentheses. Then we plug in 0. So I do want to point out one thing here. As you plug in 0 into both these expressions do not go away to 0. So 0 in for cosine doesn't go to 0, and 0 in for this exponent doesn't go to 0 either. So again, be careful with your antiderivative. Zeros is not necessarily going to always wipe that expression out for that term. Okay, so now we have everything plugged in, and now we're just going to try to simplify here. 2 cosine 0 becomes 2 times 1. The negative distributes through. We get +1 minus 2 cosine of -1, which is a value that we don't know, but we were just hold on to that as an exact value. -1/4 e to the 4th in the denominator, and then +1/4 e to the 0 becomes 1. Combine some like terms together, we get 3 plus 1/4, which is 13 over 4, minus 2 cosine of -1 minus 1 over 4 e to the 4th. Now, all this only represents this portion. There's still that average value portion, that 1 over b minus a, that's still sitting in front that we haven't included yet. So that 1/2 will now be brought down, and in addition to all the added antiderivative values that we put together. And then we can either leave it in this form or distribute the 1/2 through. Okay, and there's our average value.